Right, in this video I'm going to talk about how the computer does arithmetic, and then specifically I'm going to talk about a circuit called a half adder. Okay, but before we get to the circuit, let's have a look at how we add numbers together in binary. So we're talking about adding 2 bits, okay, because really adding numbers in binary is just if you can add 2 bits, you can add any number of bits together. So let's just have a look at what that entails. So we could have a 0 and a 0 that we add together. Okay, so if we add those 2 together, we get a 0. But that isn't the end of the story. What we actually are producing is a carry, but the carry has a value of 0. Okay, so the answer to 0 plus 0 is actually 0 carry 0. There are 3 other combinations that we could have. So we could add a 0 and a 1, so the answer to that 0 and 1 is 1 carry 0. And the reason we have to say carry 0 is because in binary you can't have a bit, the carry is a special bit, you can't have a bit that has no value. It either is a 1 or a 0. So there has been a carry or there hasn't been a carry. And when we look at assembly language, you'll see that that's like an important tool when we're doing any sort of computer-based arithmetic. So we've had 0 and 0, 0 and 1. The next one is to have 1 and 0. Add those 2 together. And that will give us 1 and 0 is 1 carry 0. And then the one that messes it all up is when we add 2 1s together. We get 1 and 1. Well, 1 and 1 is 2, but in binary that is a 0 carry a 1. Okay, so they're all the combinations of bit patterns when we're adding 2 bits together. Okay, so when we get 0, 0, we get 0, 0, 1, we get 1, 1, 0, we get 1, and 1, 1, we actually get the answer 0, but we carry a 1 over. Okay, now we can draw a truth table for this. So if we was to label each of these numbers A and B, okay, so the top set of numbers is A and the second set is B. Let's do A, B. So the patterns of bits that are possible are these. Okay, and if we look at what our outputs are, so this is our sum line. Okay, so let's have a look at what the sum is. So you can see when we got 1 and 1, we get a 0. So let's put that in. Okay, let's change the pen. If that's a bit clearer, that's better. When we get a 1 in A and a 0 in B, we get a 1. When we have a 0 in A, which is here, and a 1 in B, we get a 1. That's good. And then when we have 0 in both, we get a 0. Okay, so let's just have a look at what that is. So when they're the same, we get 0. So with 2 noughts, get 0. 2 1s, get 0 for the sum. When they're different, we get a 1. Well, that is our friend, exclusive OR. Okay, and if we're talking about a logic circuit, it looks like this. I never like drawing OR. It's a horrible shape to draw. It's an OR with an extra line. That's exclusive OR. Okay, so 2 inputs. If they're different, you get a 1. If they're the same, you get a 0. So if we look at these patterns again, but look at the carries each time. So when we got 0, 0, so A is 0, B is 0, the carry is 0. So let's just put a C. So 0. When we got 0 for A, 1 for B, which is there, we get a carry of 0. When we've got a 1 for A and a 0 for B, so that's there, we get a carry of 0. And when we get a 1 in A and a 1 in B, we get a carry of 1. Okay? And if we look at that, when we have got anything other than 2 1s, we get 0. So the only time we get an output of 1 for the carry is when both inputs are 1. That is AND. Okay, so that's got the logic symbol like a big D. So 2 inputs. If they're both the same, you get 1 as an output, otherwise you get a 0s. So we actually can create a circuit that takes 2 inputs uses an XOR gate to generate the sum and an AND gate to generate the carry. So let's try and draw that circuit. So if we do A and B, I'll draw them a bit closer together, A and B, and I just say, right, okay, those two inputs, they need to go into an exclusive OR gate, and they represent the sum. Well, we want an AND gate. Now, what you don't do on a logic diagram is you don't draw A and B again. What we do, draw your AND gate and your output, which we're calling the carry. And we need to take copies of A and B. So if we do a clear dot on the A line and draw a line down, put it into the AND gate, and a clear dot on the B line and put that into the AND gate, then we're saying basically we're sending the A and B inputs to the XOR gate and the A and B inputs to the AND gate. Okay. If the lines cross, that doesn't matter. We only show that the lines are joining by putting the dots. Otherwise you end up trying to do this and it looks horrible. No one wants to do that. That makes the diagram look stupid. Okay, so use the clear dot join notation, and that's our half adder. So that's the truth table, but that's where it comes from. So it's just from basic mathematics, but that isn't the whole of the story. This will only add a pair of bits together and produce a carry. But when we're working with numbers, let's say we add this number and we add it to this number, let's put another 0 on there. We say 0 and 1 is 1, carry 0. Then we go 1, 1 and 0 is 0, carry 1. We actually take on board the carry. So we're actually adding 3 bits together. And the half adder is not set up to do that. But there is a system called a full adder, and this will enable us to do the full bit addition. And I'll talk about that in another video. Okay? So the half adder is there. It will take 2 bits, add them together and create a sum and carry, but actually we need to do something more complicated than that to actually do the full addition, because we haven't taken the carry into account. So this will just do single bits. Okay?